To see how raw materials are deposited as thin films on the wafer's surface, let's go back to the clean room. We'll take a closer look at the simplified CMOS transistor built in Silicon Run 1. Selecting the best raw material from a wide variety of possibilities depends on the process, the equipment, and the type of film. Regardless of the type of film, certain film properties must be considered. The direction of stress, compressive or tensile, that the layer will exert on the wafer. The film's ability to adhere to the surface. The composition or chemical makeup of the film. The film's chemical compatibility with neighboring layers and subsequent processes. The film's ability to deposit evenly over all surfaces, and the ease with which the material can be deposited. After the wafers have been cleaned, they are prepared for the deposition of the first layer, a thin film of insulation. Of all the types of insulating materials available, the most commonly used for the first layer is silicon dioxide. Inside this vertical furnace, the oxidant is introduced as pure oxygen gas, or as water vapor. The silicon comes directly from the wafer's surface. The wafers are loaded onto two large quartz boats. These boats move into the hot vertical furnace slowly, allowing the wafers to adjust to the high temperature. At 850 to 1,000 degrees Celsius, pure oxygen, or water vapor, is injected from the top of the furnace tube. Unreacted gases will be exhausted from the bottom of the furnace. The oxygen or water molecules that reach the silicon wafer find enough thermal energy to break their bonds. The oxygen reacts with the surface silicon molecules to form silicon dioxide. Hydrogen, a byproduct, is exhausted from the furnace. The rate of oxidation is strongly affected by the wafer temperature and the oxidation time. When the concentration of oxygen is abundant, the silicon dioxide layer can only grow as fast as the silicon bonds are broken. This is strongly affected by temperature. The higher the temperature, the higher the oxidation rate. To produce uniform layers of oxide over the wafer's surface, the temperature of the reaction chamber must be precisely controlled. Keeping a consistent, uniform thickness over all wafers, whether single, in batches, or even from run to run, is important. This ensures electrical properties are the same throughout the wafer's surface on all wafers. Some of the electrical properties required of a good insulating film are a controlled dielectric constant that determines the amount of charge stored in adjacent conducting layers, the strength to withstand maximum voltages, and a low concentration of impurities that may store extra charge. Silicon dioxide is a high-quality glass-like insulator. It is used a number of times throughout the process to protect the silicon substrate and to electrically isolate conducting regions. After photolithography, ion implantation, and diffusion of the N-well, the thin layer of silicon dioxide damaged by ion implantation is etched. A new layer is regrown. To prevent additional growth of this new layer and protect the region where the transistors will be built, an insulation layer of silicon nitride is deposited using chemical vapor deposition, or CVD. In this process, all chemical reactants are brought in from an outside source. A gas containing silicon, such as dichlorosilane, is selected to react with a gaseous source of nitrogen, such as ammonia, to produce silicon nitride. It is easier to manage deposition when only one reactant needs precise control. Providing an abundance of ammonia, for example, ensures the complete reaction of the limited dichlorosilane. Reactant gases are usually introduced into the chamber with carrier gases, like nitrogen and hydrogen. These gases dilute the reactants to slow the deposition rate for better control. Carrier gases do not directly participate in the reaction and are carried out in the exhaust stream. Nitride deposition often takes place in a low-pressure CVD furnace. Once the cassettes are loaded, the chamber is sealed and a vacuum introduced. Under normal atmospheric pressure, surrounding gas molecules are densely packed and in constant collision. When a vacuum is introduced, most of the atmospheric gases are pumped out, leaving a lower density of molecules. Loading wafers in this vacuum helps guarantee fewer surface particles when the nitride layer is deposited.